Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So this is another video of LLM series in which we will see what is positional encoding. So in previous videos we had seen what is tokenization and specifically byte pair encoding and what is embedding and how it is used in the transformer, right? So now next step in the transformer architecture is positional encoding. So let's see what is positional encoding and why we required it, okay? So if you recall, the models which are used before the transformer are RNN or LSTM, right? So in RNN and LSTM, we are processing the series or let's suppose a text in a sequential manner, right? So for example, let's suppose our input is having 64 tokens, right? So we will process each token at once in LSTM and RNN, right? But in transformer, what we are doing, we are processing our whole input at once in parallel manner, okay? So RNN LSTM by default has the positional information of words, right? Which word arrived first and which word arrived at late in the sentence, right? And we know when we are processing any sentence or natural language, the order of each words must be used, right? Because without order of each word, the sentence meaning might be changed, right? So that's why we required some encoding or some technique by which we can tell our model that these words arrive first and these words arrive in the later in the sentence, right? So that's why positional encoding is required. So now let's see how we can provide a positional information of each word to the model, okay? So I just listed a few ways by which we can provide the positional encoding and the drawback, right? So we can just get the better context like why they are using this kind of positional encoding in this model, right? So first of all, first approach will be a simplest form, which is can be we will train our model with positional encoding, right? So in previous video we had seen that we are learning embeddings from the token during the training, right? So same way, why don't learn positional encoding as well during the training, right? So there are few limitations of this approach. First can be a maximum sequence length constraint, right? So for example, let's suppose you had built one model with input length 128, okay? So now this positional encoding which you had learned during the training cannot be used with input size of let's suppose 129, okay, or 140, because these are trained with the model and we don't have the information like how to encode 140th word, right? So we cannot generalize this positional encoding over the sequence length if we train it or learn during the training, right? So this is one of the drawback. That's why we cannot utilize it. Of course, if you want to learn during the training, you need to train your model again. For example, you had trained one model with 128 input size and you are good to go, right? You have your positional encoding and you can train it and you got that matrix, simple, as we are doing for the embedding. But if you want your model can perform with let's suppose 140 input length, then you need to retrain your model again, right? So this can be one of the drawback. The second thing or second way in which we can use sine function, okay? So the concept here is let's use sine function and concatenate that value with our embedding, right? So what we are saying here basically, let's suppose we are using one sine function with some scale. Let's suppose scale is 4, so our function will be sine of let's suppose position divided by 4, okay? So position is nothing but our position of the word, right? So for example, there is a word, let's say uh, simple, let's suppose I am writing I am Chirag, right? Then this is 0th position, this is 1st position and this is 2nd position, right? So this scale is nothing but which will control a frequency of your sine function, simple, right? So for first word, what I will use, sine of 0 divided by 4, sine of 1 divided by 4 and sine of 2 divided by 4 for the third one, right? Simple. And whatever value we will receive, we will concatenate it with our embedding. So let's suppose there is a first word or first token has this embedding, right? And sine of 0 is 0, simple, right? So we will add, not adding, basically we are concatenating 0 at the end of that embedding. So now my embedding will look like this. And for second position also we will add the value of that function which is written by the sine function and concatenating with embedding, right? So same we can do for next positions as well, right? But here also one drawback. We all know sine and cosine functions are periodic function, right? So after some point they will repeat the value, right? So let's suppose sine 0 is here, and after this point the value will be repeated. If you see this point and these points have same value, right? In this scale is equal to 4, in this function if you say we can have value, unique values till 24 or 25. After that it will repeat itself. That means there is no unique value after a certain point, right? It is the nature of sine or cosine functions, right? They are periodic function, they will repeat itself, right, at one after one cycle, right? So one thing we can do to avoid this, let's use another sine function or cosine function. Let's suppose here we are using sine of position of 4, right? Position divided by 4. Let's use second function which can be position divided by 5, let's suppose, right? And instead of concatenating only one, we will concatenate these two as well. So now for example my embedding size is 5 and 2, and I will concatenate these two sine values, let's suppose here. Then my embedding size will be 5 and 4, right? Still if we use a 2 sine function, still after some point it will repeat itself, but there will be a larger number than the 25. Same way we can increase a number of functions which we can concatenate with our embedding to provide position information, right? This makes sense. We will have unique value at the end and it will provide a position information. But what is the drawback of this point is we are concatenating this information which are related to the position, which will change our embeddings, right? Because as I say in the self attention, in the next video we will learn the self attention. We need to multiply this matrix with someone, right? We need to multiply embeddings with some matrices, right? So if we concatenate this value, let's suppose we use 5 sine function at the end and concatenated with our embedding, then our embedding size will be, let's suppose, 5 and 7, right? So when we multiply this embeddings with some matrix, we are multiplying this as well, right? The positional encoding as well, right? Which is not we want, because the model should learn embeddings, right? Self attention will focus on each word, which word we need to focus. For example, what is the work of self attention? I'm just providing you some context here, okay? So for example, when we are writing, let's suppose dog is hungry, so it is angry, okay? So this it refers to this dog, right? So this is the task of self attention, that it will relate each word with each other and find what is the most related word for each, right? Basically pairing. So this it is related to dog. So by human we can understand it very simply, right? But to explain the model we require self attention. Don't worry if you are not getting correctly currently, we will learn in the next video in very much detail, okay? So if we concatenate this value, if we are concatenating these two values with our embeddings, we might change a response of self attention. And second thing, we are adding a complexity as well, all right? So now for example, before our model need to process 5 and 2 dimension, now our model will need to process 5 and 7 dimension, right? So there are two two drawback of this function or this way is we are increasing our length of dimension, which will lead to increase the complexity of model. And second, when we perform with the self attention, this positional encoding will be also multiply and might change the result, right? Which we don't want basically. We just want the positional encoding to provide the information about the position. It is not related to any word, right? For example, we have the embeddings of dog and we are adding this let's suppose 2 or 5 sign values which are not related to the dog but they are related to a position, right? So this is the two drawback of this function, right? So yeah, this graph is basically showing like can use sine x by 5 and sine x by 2. These two kind of graph will be there, and we will use, let's suppose for 0 we will use this value, for 1 this 2 value we will find and we will utilize, right? So after some larger value we can get the repetitive values for this two vector, you can say, right? Which will be a sine x by 5 and let's suppose sine x by 2, right? So now let's see, this is the context, right? So why sine and cosine functions are used. So now let's see the actual positional encoding in transformer, right? Okay, so as we learn, one drawback is we are concatenating the value which will increase the length, right? So one of the way to solve that, instead of concatenating, let's add this value, right? So if we add something in 512, it will be less, length will be 512 itself, right? So we are not increasing the complexity here of our model, right? So now let's see what they are suggesting. So these are the formulas they are using to perform positional encoding, which is used in the transformer and introduced in the paper. Attention is all you need. Okay, so now let's understand this, the position encoding function, right? So what we are doing here, instead of concatenating, we are adding, and second thing, we are adding element wise. Okay, so for example, let's suppose I have a 512 dimension. Let's suppose this is 1 cross 512. Our one embeddings for, let's suppose, a one word, let's suppose it's woo. For woo word we have 1 cross 512 dimension. So we will calculate this formula for each position, not the position, let's rephrase it, for the each index. The position, that means the word position, and index means the index of in embeddings. Okay, so this is the 0th index in the embedding for one word. Okay, so we are adding here something here, and we are adding for each 5 and 12 indexes. Okay, so let's see how we are adding. So what they are suggesting, for position 2i, so basically for each even position we will use sine function, and for each odd position we will use cos function. Okay, this position is nothing but a position of our word. Okay, so in this sentence, for example, let's suppose this sentence positional encoding method used in the transformer. So this is 0th position, this is 1, 2, 3, 4 kind of, right? So this is the position, and this is 2i. So I is nothing but a index in word embedding, right? So for each word we have 5 and 2 vector, right? So this 5 and 2 basically a index, right? So 0, 1, 2, 3, 4, this will be our index. So what we are doing, okay, let me write here. So for example, let's suppose we are processing one let's suppose we have 3 words. Okay, simple. I am Chirag. So now for I will have 5 and 2 vectors, size of vector. For M I will have the vector size 5 and 2. For Chirag I will have vector size of 5 and 2. These are nothing but embeddings. Okay, let me write here embeddings, right? For each token we have these embeddings, and this embeddings has size 5 and 2. So here, let's suppose we are adding positional information for first token here. So what we will do, at 0th position, as it is even, right? Let's suppose it is even basically, okay. So we will use sine function here, cos function, sine function, cos function, right? And this is 10,000 is a constant. Let's suppose the D model is nothing but a embedding size. So D model will be also constant over the model, right? So D model, however, will be, let's suppose 512, right? This will change and this will change. Everything is constant here in the formula. Just position and the dimension index will be changed, right? And for second position, we will have position is equal to 2. Okay. Here we will position is equal to 2 and index will be changed. So here is also position is equal to, sorry, position will be 1 here and position will be 2 here. Okay. Right. And we will change the indexes and get the value. So for each even position we will use sine, for each cos, for each odd position we will use cos, right? Hence we can say here we are using, if our embedding size is 512, we are using 512 cos and sine functions, right? And these are not learned during the training. You can extend it till any number of input sequence, right? Because these are just functions. We are not learning here anything, right? And this will provide a uniqueness as well, right? So that's why they are using this function. So if you see just a diagram, this diagram you had seen at multiple places, right? In this diagram, if you see, this is the vector which we found by applying this positional encoding for the first position, let's suppose. This is for second and this is for 200, right? So this will be whole vector, okay. So what we are doing here, just simply, first we will calculate our vector by using sine and cosine function as our embedding size, right? So let's suppose our embedding size is equal to 512. We will calculate another vector which will be the positional encoding, same size 512 for first position, and we will add, okay. Same for the whole sequence according to the position, right? So if you see in this diagram, at the later indexes, right, we are having very less change in the values, right? So here are very drastic change, right? So at the end we have the higher frequencies, so values will be very small change, okay. And when we have initial, we have this kind of curve, okay. So values will change the faster at the initial index, and values will change very slow, or you can say very small margin in each values. These values are very different, okay. So if you see 59 and 60 will have very different value but very small change. For example, let's suppose 59 has 0.5, then 60 will have, let's suppose, 0.51, something like that, okay. Just hypothetically, something like this, the value change will be very smaller but values will be the different, okay. So this is how these metrics are generated, okay. And one more thing, as we are using sine and cosine functions here, the researcher, they are saying, for example, there will, this is the first position, this is second, and this is 200, okay. So if you have this second positional embeddings, there will be a way of using linear transformation. You can reach at the 200th position encoding, okay, the position encoding for 200 position number, okay. So each positional vector, or you can say positional encoding vector, you can achieve by linear transformation. So what that means, there will be some matrix, let's suppose W. If you multiply it with 1, you can achieve the positional encoding for position 2, and so on. So there will be some linear relationship between each and every encoding vectors, okay. Hence the model can learn the positional encoding with embeddings, okay. So we are not going to much depth for the math, but you can just think it as a there will be a linear transformation or linear relationship. You can find it out. Okay, from if there will be one matrix, if you have a position encoding vector for position 200, you can find for 400 as well. Okay, so now let's see what are the advantages of this. So first is it is easy here to model to distinguish between okay what is positional encoding and what is embedding. As you can, as we had seen, they have unique values for each vectors, right? And it is also has a linear transformation mechanism, okay, or linear transformation what you say characteristic. Okay, second thing, the model can be generalized to longer sequences because we are not learning here anything, right? It is not model dependent. It is simply a functions which we are adding. So for example, you are training a model with sequence length 512, you can use the same function. And if you are training a model with 1024, or you can say like you are changing the sequence length, this encoding technique will work out of the box, right? Because it is not dependent on a sequence length or on a model. It is not part of the model basically. It are simple functions, right? And we are adding them element wise, so we are not increasing our embedding dimension, right? If we are concatenating, let's suppose if we are using 512 sine and cosine function, right, then our 512 embedding will be converted into 1024, right? Embeddings will be much larger and our model complexity will also increase. Just we want to add positional information, right? We cannot increase the complexity this much, so we are adding into it, hence it will be same as our original embedding size 512, right? So this is how positional encoding is added into the model and why we are adding basically. Okay, right? So this is all about the positional encoding. If you like this video, please press the like button and subscribe my channel for upcoming video, as in next video we will see what is self attention in detail, right? Thank you.